Hello everyone, good afternoon. Myself Priya, Industry Relationship Coordinator at Takshila VLSA Technologies. Welcome to today's VLSA webinar. Before we start, I would like to give a brief introduction about our institute. We Takshila Institute is a leading VLSA training center in Bangalore and Hyderabad. We offer special courses helps you learn important skills in a VLSA field. We offer physical design, analog layout design, analog circuit design, ASIC verification, and design for test. Why to choose Takshila? Here are some of our unique features. We provide 24/7 tool access and VPN support for continuous practice. Hard copy materials are provided to enhance your learning experience. Experienced trainers. Our trainers have over 10 plus years of industry experience. Placement support. We offer 100% placement assistance until you secure a job in a VLSA semiconductor industry. Our candidates have secured positions with leading companies such as Micron, Synopsys, Intel, Insemi, Onsemi, Wipro, etc. Today's webinar will be presented by Apporva ma'am. Ma'am have over 5 plus years of industry experience and currently working as a physical design engineer. Now I will hand over this session to Apporva ma'am to continue the webinar. Thank you.
Hello everyone, good afternoon. I am Apurva, currently working as a physical design engineer in a well-known company with over 5 plus years of experience. I have worked on a various stages of the physical design flow like floor planning, placement, CTS and routing, timing closure using the industry standard tools such as an ICC2, ICC, Prime Time and SRRC. I'm also a mentor at Takshila VLSA where I support the students and guide them towards the career in a VLSA industry. So in today's session, I will be taking you through the webinar on job opportunities in VLSA semiconductor industry. So let's get started. So these are the topics we are discussing today in this webinar. So first one is in a VLSI semiconductor industry. So we'll learn what is mean by VLSI semiconductor industry is there. So how the growth will be there. So what is eligibility criteria is there. So we'll discuss. And after that we will discuss about Takshila VLSI course offered and unique features, core job opportunities, industry salary scope, placement at Takshila VLSI. So after this we will learn some technical part. So in the technical part, you will get to know what is meant by AMS and custom IC layout design flow, ASIC or a chip design flow, RTL design and verification concept, physical design flow, and lastly we'll discuss question and answer. So if you have any doubts means, so you can ask the questions. So terminology. So these are the few words are there. So these words we are using in our entire VLSI industry. So first one is in a semiconductor. So what is meant by semiconductors? So semiconductors are lies in between the conductors and insulators. So you know that in the semiconductors we are having the P-type semiconductors. So N-type semiconductors. For the semiconductors, so when you provide that external energy for the semiconductor, so they behave as a conductor. So in the pure form of the semiconductor, so they behave as an insulator. So that's why we call the semiconductors are in between the conductors and insulators. So and using the semiconductors, we are forming the diodes, so transistors. So in the transistors, we have the BJTs, MOSFETs, so and CMOS, PINPETs. So PINPETs are now we are using. So this all will be we are designed using a semiconductor. So using this only we have to do the fabrication of the IC. So then IC will be fabricated using the semiconductors. And after that we have the VLSI. So very large scale integration. So whatever IC we are using, so in that IC to design our IC or to fabricate that one IC, so we are using billion of the transistors. So that's why it is called as a VLSI. So before we are not using billion of the transistors. So at the starting means when IC is invented, so that time we were is 5,000 of the transistors. So this one is called in a small scale integration. After that we are start using like lack of the transistors. So that is called as a medium scale integration. After that, we are start using the million of the transistors. So that one is called as a large scale integration. So now we are using billion of the transistors. So that's why it is called as a very large scale integration. So after that, we have the chip or IC, integrated circuit. ASIC. ASIC means application specific integrated circuit. So whatever IC is there, so that is that particular function. For example, if you take mobile means, so mobile is for the particular function. So we can't use that mobile IC to the other applications like any other automobiles or any other applications we can't use. So that's why it is called as an application specific integrated circuit. So where the chip or ICs are used. So in our day-to-day activity, we are using a lot of the electronic equipments. So in all the electronic equipments, we are using an IC. For example, we are using mobile, laptop, TV, satellite, cars. So even in a small calculators also, we are using an ICs. How a chip will be looks like. So this will be the interior looks of the IC. So when you saw that IC, so first you will observe black color box outside. So for example, you can see here in this diagram. So here one IC is there. So this one is one IC. So this one. So this one IC. So these all are the ICs. But when you see that IC, so you will not see that internal structure, means that how that circuits will be connected. So you will not see. So first you will see that this plastic cover. So that is called in a plastic package. So why we use plastic package? So it won't allow the damage of an IC from the external sources. So that's why we are using a plastic package. And that plastic package is inside that plastic package that IC will be there, or a semiconductor die, the IC. And the inputs and outputs of the ICs are a golden bonds. So we use the gold material to connect the inputs and outputs. So why only gold? So we have aluminum, copper, and another metal layers are there. So why only gold we use means, so compared to all the conducting materials, so gold is in a very good conducting material. So that's why we are using a gold. And this gold bonds wires are connected to these external pins. So these external pins will be communicate with the external circuit. So you see this one only. So this pins only you will see. So this pins will be not visible. So you may ask the question, so this gold bonds only we can directly connect it to the external circuit. So why in between this again external pins? So if you directly connect with this gold bonds to the external circuit, so any voltage fluctuation or a current fluctuation or a sudden change in the function, anything will be happen means the IC will be damaged. So that's why to protect that one, first we have to connect with the external pins, and that external pins are connected with the external circuit. So semiconductor wafer. So what is meant by semiconductor wafer? So it is basically silicon material die. So on this only we have to do the fabrication of the IC. It is maybe a P-type silicon material or a N-type. So why only silicon? So we have germanium also, right? So why only silicon? So silicon is easily available in the nature. So you know that sand, from the sand only we are collecting the silicon. So what we do, so we will collect the sand, and in that sand, so we'll separate that silicon and waste materials. After separating, so that silicon will be created like this one material. So it will be like this. So after that, we will cut the silicon small pieces like this. So one piece, so taken as an wafer, and on that only we have to do the fabrication of the IC. So you can observe here small square like structures are there. So one square like structure is one IC. Like that, number of the ICs are fabricated on the wafer at the same time for the different applications. So you know that. So ICs are fabricated using a CMOS or a MOSFETs. CMOS or a MOSFETs. So how we have to draw the CMOS structure. So you know that one. So first we have to take one P substrate. So on this P substrate, we have to create one N well. So here one P diffusions are there. So this is an N well. Here P plus. Here N plus. So like this we have to create, and on this we have to create the gate. So whatever that these transitions and this gate connections or metal connections, so everything will be happen in this P substrate. So this P substrate is a wafer. On that, all the MOSFETs, all the CMOS will be created on the wafer. The size of the wafer will be 12-inch wafer. So after that, how many chips are integrated? So when IC is invented, so that time we were is 5,000 of the transistors in a one IC. So now we are using thousands of the transistors. So in a one IC. So this is a CMOS structure. So already explained you. So introduction about the Moore's law. So what is mean by Moore's law? So when you start learning about the VLSI semiconductor industry, so first you will learn Moore's law. So this Moore's law will be stated by the Gordon Moore. He is a co-founder of Fairchild Semiconductor. So according to him, every 2 years number of the transistors will be doubled. So for example, this year you are using 8 transistors, means after 2 years it will be doubled. So 8 means 16 transistors we have to use. Like that, every 2 years the number of the transistors will be doubled. So this graph is according to the Moore's law from 1971 to 2018. So in the graph you can observe there, first one is in the 1970, the number of the transistors will be 5,000. So the number of the transistors are 5,000. So the IC name called Intel 8008. So after 2 years, means in the 1972 the number of the transistors are 10,000. So it doubled, 5,000 to 10,000. And after in the 1974, 50,000 we were used. After that 1 lakh it will be doubled, 5 lakh to 10 lakh, 50 lakh to 1 crore. Like that, every 2 years the number of the transistors will be doubled, and the number of the transistors will be doubled. So in the 2018, so we were used 50 billion of the transistors. So now we are using 100 billion or more that transistors. So now also we are increasing the number of the transistors in the ICs. So how it will be increases? So how the technology improving, like that we are reducing the size of the transistors. So for example, one area is there, 1 meter square area. So you are placing 20 transistors. So in that area you are placing 20 transistors. So what happened if you reduce the size of the transistors means, so this is an area we have. So in this area, it is 1 meter square area. So this area you are placing 20 transistors. So like this you are placed. So when you reduce the half of the size of these transistors, then automatically the number of the transistors will be doubled. So in place of 1 transistors, 2 transistors will be placed like this. So then number of the transistors are doubled, 20 to 40. So we are increasing number of the transistors. So what happen if that transistors count will be less, means that more functionality work it can't be do by the IC. So that more transistors will be there. So it will be do entire transistors in a one entire function in a one IC only. So that's why we are reducing the size of the transistors. So how we are reducing? So that process is called as a MOSFET scaling. So according to the voltage and current, we are reducing the size of the transistors. So these all are the process nodes. So process nodes means these are the size of the transistors, also called as technology nodes. So whatever in the industry also you may hear that. So some employees will be say that we worked on a 7 nanometer technology, so 3 nanometer technology. So I will explain what is meant by technology in the next slide. So in the 1971 we were 10 micrometer technology. So 1 micrometer means it's a 1 millionth of the meter. So the small ICs or small transistors we are used in the 1971. And in the 1981, 1.5 micrometer, 1987, 800 nanometer. So 1 nanometer means it's 1 billionth of the meter. So micrometer to nanometer we reduced. And in 2001, 130 nanometer we were used. In the 12, 22 nanometer, 18, 7 nanometer, 22, 3 nanometer, 24, 2 nanometer. So nowadays in the industry we are using 1.8 nanometer. So in the future we may use 1 nanometer, 0.5, 0.2 and below this also. Like that scaling will be happening nowadays in the industry. So what is technology node or tech node? So I says that we will call as we worked on a 3 nanometer technologies, 7 nanometer technology, like that. So what is mean by the technology? So this is a drain. So this is a source. So we have the gate here. So whatever the distance is there in between the source and drain, so that is called as a tech node or a technology node. So typically tech nodes used in the productions are 28 nanometer, 32, 45, 65 and 90 nanometer. So this is called as a MOSFET technology. So these projects are easily available. So this is called as a MOSFET technology. So why we call it as a MOSFET means, so whatever the ICs we are fabricating, so this ICs 20 nanometer, 32, 45, 65, 90 nanometer. So the to manufacture that IC we are using in a MOSFET manufacturing process. So that's why we are called as a MOSFET technology. So nowadays in the industry we are using below 28 nanometer technology. So like 3 nanometer, 5 nanometer, 7 nanometer, 14 nanometer. So that is called as a FinFET technology. So FinFET is an advanced version of the MOSFETs. So what happens when you reduce the size of the transistors, we are getting more dropbacks by using the MOSFETs. So that's why we switch from MOSFET to the FinFET technology. So it will be help to increase the reduce the power dissipation and delay also less, and some area occupied by the FinFET also less compared to the MOSFETs. So it has a more advantage over the MOSFET. So that's why to fabricate the IC, we are using a FinFET technology. So that will be about the technology node or tech node. So semiconductor industry demand drivers. So where the semiconductor ICs are used and which market increase the demand of the ICs. So in the computing stage, we are using 34% of the ICs. So in the computing means in the web servers, in the data servers, we are using an IC. So there we are using an semiconductor industry. So there we are using 34% of the ICs, and wireless communication and in the consumers. So consumers means, so we are using the laptops and mobiles. So we only comes in the consumer stage. So we are using 14% of the ICs. In the autos, industrial, we are using 8% of the ICs, and wired communication, even in the military and aerospace also, we are using an ICs. So VLSI semiconductor industry growth. So every year the growth of the VLSI industry is, so 8.6% is there. So that is in a compound annual growth rate. In 2023, the growth of the VLSI industry is $544.78 billion. And in the 2024, it is $584.17 billion. And in the 2025, it is 500 in the 25 it is $627.76 billion. So after 10 years, means in the 2033, it will be $1,137.57 billion. So like that, every that you can observe here by this graph, every year the growth of the VLSI industries increases year by year, and the opportunities also increase in the VLSI industry. So what are the companies are there in the VLSI semiconductor industry? So you learn that so how the growth will be there. So where we use that ICs and all, but where we are fabricating and where that ICs will be developed. So we have to learn that one also. So what are the companies are there? So whatever the companies are there in the VLSI or semiconductor industry, so that all the companies, so mainly we are categorized into three types. So one is a product based company, EDA companies, and service-based companies. So what is mean by product-based companies? The main project and fabrication of the chip will be done in the product-based companies. So, and EDA companies means, so whatever these projects we have to do means, I said that 3 nanometer technology ICs are there, 5 nanometer technology are there. So for that one, we have one particularly project. So to design that project, so before going to manufacture of an IC, that IC we have to develop in a software. So that software called as a tools. So that will be provided by the EDA companies. And service-based companies, as the name suggests, it gives a service to the EDA companies and the product-based companies. So EDA product-based companies always be sync up to meet the technology developers with the support of the VLSI engineer. So if any one company is not there, then the VLSI project will be not completed. So these are the three main categories will be there in the VLSI or semiconductor companies. So semiconductor ecosystem. So this classification will be done based on the work of the company or functionality of the company. So first one we have the fabless chip firms. So what is meant by fabless chip firms? So whatever the companies are comes under the fabless chip firms, they will design their project, but that companies don't have their fabrication process. So for example, some all the fab companies are there, so that all the product based companies or the fabrication companies, so they have their own fabrication steps. So they have to follow their own fabrication steps. So in the fabless chip firms, what happens? They don't have any fabrication process. So they have to take the fabrication process from the another company. For example, it is Qualcomm is a, so Qualcomm is designing their project. So it don't have their own fabrication process. So they have to take the fabrication process from the TSMC company. So using that TSMC company fabrication process, it has to design their project. So that's what is called as a fabless chip firms. So after that, we have the foundries. So what is mean by foundries? The main fabrication of the chip will be done in the foundry. So whatever the projects will be done in the fabless chip firms or any other companies, that all the projects will be fabricated in the foundry. So we have the TSMC, so Samsung, SMIC, UMC, Global Foundry. So these all are the foundries. And come to fabless non-chip firms. So fabless non-chip firms. So these are the companies are comes under the software companies. So you may ask the questions where they use the VLSI semiconductor industry. So in the computing stage, we are using the VLSI semiconductor industry. So there we are using the ICs. So that's why these companies are called as fabless non-chip firms. So we have the Apple, Google, Microsoft, Amazon, IBM, Meta. So these all are the fabless non-chip firms. And IP and design software. So these are the companies will provide the tools. So like a Synopsys, Siemens, ARM, Cadence, Ensys. So mental graphics also there. So their companies will provide the tools. So tool or a software. And equipment providing companies, we have the Kelvin, ASML, Tokyo Electronics, Applied Materials, Lam Research. So these all are the equipment providing companies. And integrated device manufacturers company, we have the Textile Instrument, Analog Devices, Infineon, Micron, Intel, Samsung. So these all are the integrated device manufacturers company. So after the manufacture of the IC, so that IC must be tested before giving to the customer or giving to the market. So first we have to test that it will be correct working or not. That one will be done by the company is called testing, packaging and assembly. So we have the TER company, America Technology, Agilent, Lattice Semiconductor and Foxconn. So these are the companies will comes under the testing, packaging and assembly. So top semiconductor product based companies. So in the 2023, the revenue is $545 billion is there. So I already explained. So in that, Intel has a 9.4 percentage and NVIDIA has a 9 percentage. And also NVIDIA shared on a triple share of the revenue at the end of the year. And we have the Samsung 8.1, Qualcomm 5.7, Broadcom, AMD, Apple, Texas Instrument, Sony, onsemi. So these all are the top semiconductor product based companies. So EDA or CAD companies. So already said that EDA or CAD companies will provide the tools. So tool is a software which is used to design an IC. So EDA means electronic design automation. So whatever the functionality or feature we want to do the design of the IC, so that all the feature will be there in the EDA tool. So using that tool only we have to do the design of the IC. And CAD. So you may ask the question where we use the CAD. So CAD means computer aided design. So while doing the design of the IC, so that IC we are observing the 2D and 3D form. So to see that one we are using in a CAD. And every steps to design the IC, so we require different EDA tools. There is no tool such as it will be there is no one tool is there, so such as it can be do every work from the starting to up to packaging. So it will be do every work. No, like that any tool is not there. So for the every steps we require the different tools from the different company. So I will explain what are the tools we are using. So then the tools are from the which company I will explain. So we are using a tools called ICC2. So before this we are use ICC and Innova's Fusion Compiler. And so other than this we have tools called ICV and Calibre, Ashura. So these are the main tools we have to use. So in between the designing, so we are using tools called Prime Time, Star RC, DC Compiler, genus, and so Red Hawk. So to design the IC, so we are using any one of these tools. After that designing, so to verify, so using any one of these tools. So ICC, ICC2 and Fusion Compiler. So these three tools from the Synopsys, and Innovas is from the Cadence, and ICV, Calibre, Assura. So these tools we have to use to verifying the design. So ICV is from the Synopsys, Calibre and Assura is from the Cadence. So and Prime Time, so and Star RC. So these are used in between the design to verify the timing. So timing check. So we have to do the prime time and star RC, and DC compiler, genus. So these are used to do synthesis process. So while explaining the technical part, I will tell you what is meant by synthesis. So DC compiler is from the Synopsys company, and genus is from the Cadence. So and Red Hawk is there. So this Calibre is from the Mentor Graphics. Sorry, I said that Cadence. So it is Mentor Graphics. So Mentor Graphics. So that Mentor Graphics company only deals with the verification stage, not a design of the IC. So these all the tools we have to use from the different companies. So you may use that ICC2, or otherwise you can use in Fusion Compiler, or you can use Innovas. Any one tool we have to use. So these are the tools are there in the to design the ICs. So fab companies. So what are the fab companies are they? So we have a lot of the fab companies. In that all the fab companies, we have the two top fab companies. One is a TSMC, Taiwan Semiconductor Manufacture Company. Other one is a Global Foundries. So every product-based company have their own fabrication process and own fabrication steps. So based on that only they will do the fabrication of the IC. So I already said. So some companies are fabless. For example, Qualcomm. So what is called as in a fabless? So already explained in the previous slide. So top fabs worldwide. So we have the lot of the fab companies. In the top fabs companies are like TSMC. So and it has a $16.78 billion revenue is there in the 2023. DMC, PSMC, Global Foundries, Teva Semiconductor, SMIC, Hi, Samsung, DB. So these all are the top fabs companies worldwide. So 500 plus established VLSI service companies. So in the service company, mainly we have the three types of service-based companies: MN service-based, large service-based, and setup service-based. In the MN service-based company, we have the Capgemini, L&T, HCL, Tech Mahindra. In the large service-based company, we have the Mirapra, Insemi, TrueChip, Excel VLSI, LeadSoc, and Vaporspace. In the setup service-based company, we have the Luxus Semiconductor, Bitsilica, Synopsys Semiconductor, TrueChip, SmartSoc. Other than this, 500 plus more service companies are there in a Bangalore and Hyderabad location. So these service-based companies hire the students and give the 6 months of the industrial training. So after the training, they will assign one project from the MNC companies or a product-based companies. So we have to go there and we have to work on that project. So after completing that project, again they will assign another project from the other company. So that process will be there in the service-based companies. So we have one small video about semiconductor IC making video. So after seeing this video, you will get to know how the fabrication of an IC will be done. So how they will do the packaging, how they will do the testing. So everything will be there in this video. So we'll see that one.
Memory chip design is the first step in the production of Micron's memory chips. This process involves the use of computer-aided design tools to lay out billions of electronic components that store data on the chip according to the product design specification. During technology development, specific process steps are defined and integrated into a process flow that will build the memory chips. The process steps are tested and refined until the process node is qualified and ramped in manufacturing. Individual memory chips, or die, are built upon pure silicon wafers in a fabrication area, or fab. fabs are state-of-the-art clean rooms that are 100 times cleaner than a hospital operating room to ensure silicon wafers are protected from ambient contamination. Among the many process areas in a fab, the photolithography area coats wafers with a photoresistant material. Then, like film in a camera, circuit patterns are exposed and excess material is rinsed away. The paths in these circuits are 5,000 times narrower than a human hair. Wafers are moved between different tools and processes using a robotic automated material handling system, or AMHS. Each wafer may be moved through more than 1,000 processes. It takes more than 1 month to make a memory chip. In probe, initial functionality tests are performed on each die on the wafer. A probe card positions probe needles onto each die to send and receive test data. This information is used to generate a map of all the die on each wafer. Only good die that pass all tests in probe will continue through the manufacturing process. In assembly, wafers are first thinned, attached to an adhesive backing, and then diced into individual die using a diamond edge saw. Using the wafer map that was created in probe, individual die are picked from the wafer, then placed on a circuit board. A solid gold wire is used to connect each chip to the circuit board. A molding process encapsulates each die in a protective plastic package and shipped to test. Every memory chip Micron manufactures undergoes hundreds of tests to ensure it meets the highest quality standards. Proprietary Ambix testers subject finished parts to extreme temperatures and conditions to force any weak components to fail before they reach our customers. Additional test equipment verifies that each part meets or exceeds its speed and performance specifications. All qualified parts are laser marked with part numbers and other identifying information. Each memory chip is optically scanned to verify strict fit and form specifications. Components are placed into industry-standard anti-static packaging and placed into boxes for shipment. Many of Micron's finished parts are used to build memory modules and solid-state drives. Automated surface mount assembly equipment is used to mount memory and other components to printed circuit boards. All products are tested using proprietary Micron memory module and SSD test equipment. Finished products are placed into anti-static packaging before boxing for shipment to the customer.
So this is a video we have from the Micron company. So after that, eligibility criteria for VLSI jobs. To get the job in the VLSI industry means the students must be completed their BTech in EEE, ECE, and TC and EIE with a 60% of the minimum percentage. So and any one VLSI course must be completed. And for the MTech students, they completed their MTech in a VLSI embedded electronics with the 60% of the minimum percentage. And any one VLSI course must be completed. So that is an eligibility criteria is there for the VLSI jobs. So about Takshila VLSI technology. So our institute is a best VLSI institute in a Bangalore and Hyderabad location for freshers and working professional. For advanced VLSI studies with a 100% placement assistant till get placed. And industry standard EDA tools and 24/7 tool support is there. So whatever the tools using in the industry, so that tools we are using here for the practice in the lab. And faculty and trainers are with a minimum 15 plus years of experience in a semiconductor domain and collaborated with the 200 plus hiring companies. So 100% placement with the training material and mock interviews. Track record of the placement to the scholarship facility will be there. So why to select Takshila VLSI? Because we have some unique feature. So we'll provide the 100% placement guarantee. 24/7 lab support is there with the experienced trainers, and low price and scholarship facility will be there. Industry standard course syllabus 100% placement assistance, industry standard course curriculum, 24/7 lab support is there, low cost value for the money. So that will be about our institute. So it is an infrastructures and labs in the Bangalore location. So these all are the classes and labs will be there in the Bangalore location. So these all also classes and labs will be there in the Bangalore location. So this is an infrastructures and labs in the Hyderabad location. So our branch is there in the Hyderabad location also. So there also class and labs will be there. So that will be about the Hyderabad location. So we have one small video about Takshila VLSI corporate video. So we'll see that one. So courses offered offline and online. So in our institute, mainly we have the 5 courses. So in the VLSI also we have the branches. So in that we are having the physical design, so ASIC verification, analog layout design, design for test, and analog circuit design. So these 5 courses are there in our institute. So training methodology and intake for the physical design, DFT and ASIC verification. For these 3 courses, the duration will be 5 months. So the duration will be 5 months and daily 2 hours class and lab practice with the full-time mentor, and number of the students are 15 to 30 and 24/7 VPN lab access is there, and LMS portal access will be there, and 15 plus experience Takshila VLSI, full-time trainer and full-time mentor, and 100% placement assistant till get placed. And for the analog layout design course, the everything will be same, but duration will be 4 months. And daily 2 hours class and lab practice with a full-time mentor. Number of the students are 15 to 25, 24/7 VPN lab access is there, LMS portal access will be there. And analog circuit design, the duration will be 14 weeks. So it is in a weekend batch, 6 hours per week class and lab practice. Number of the students are 10 to 15 and 24/7 VPN lab access is there. LMS portal access will be there, and 15 plus experience Takshila VLSI full-time trainer and 100% placement assistant till get placed. So this is a training methodology and intake is there in our institute. So core job opportunities in PD. So you may ask the question, so after completing the every course, so what are the jobs I may get? So after completing your physical design course, so you get the job as a physical design engineer. So where we have to do the design of an IC. So that entire IC will be designed in the physical design. So after that, other than that, so you get the job as an ST engineer. So STA is a part of the physical design. So where we have in the STA, we have to do the timing analysis. So STA long form is static timing analysis. So in the STA, we have to do the timing analysis, and you may get the job as a physical verification engineer. So we are designing the IC. For that IC, we have to verify that IC. So that one will be done in the physical verification engineers. And after that, you may get the job as an EM, IR sign off engineer. So EM and IR. So these two are the violations we get after the design of the IC. So EM means electro migration, IR means voltage drop. So EM means so when explaining the technical part, I will explain you what is meant by EM and IR. So that EM, it will be more means, so it will be directly damage the IC. We have the formula for the electromigration. So according to that formula, that electromigration violation will be directly proportional to the damage of an IC. So that's why if that electromigration is more meant, it will be directly affect to the IC only. So that's why we have to reduce that violation. So that one will be done by this EMIR sign up engineers, and you may get the job as a methodology and flow engineer. So these jobs are comes under the physical design course. And after completing your analog layout design course, so you may get the job as an analog layout design engineer. So for the entire design, so you have to design the layout, and you may get the job as an standard cell layout design engineers. For the particularly for the standard cells, we have to design the layout. So standard cells means, so we have whatever we have the AND gate, OR gate, whatever that basics gates are there. So including basics gates and flip flops, so that all will be comes in the standard cell. So that we for that standard cells we have to design the layout. And you may get the job as an IO layout design engineer. So IO means it is an input and output. And you may get a job as a memory layout design engineer. For the particularly memory, you have to design the layout, and RF layout design engineer. So these all the jobs will be comes under the analog layout and design course. So after completing your ASIC design and verification course, so this is a front end. So after completing this course, so you may get the job as an ASIC verification engineer. So in the ASIC or FPGA RTL, so these three are same only. So after in this, so we have to write the code. So in the ASIC or FPGA RTL design engineer, so that you may get the job. So that code will be verified in the this ASIC verification engineers. So that you may get the job. And IP verification engineer, UVM verification engineer. So these jobs are comes under the ASIC design and verification course. So industry salary and scope. So after completing your course, so you get the job as a freshers. As a freshers, that starting package will be the 4 to 6 lakhs. So that is a minimum package. And with the 3+ years of experience, so you get the offer letter from the product-based companies like Intel, Samsung, so Synopsys, Cadence, like that. You may get the job. You may get the offer letters, and with a package of 15 to 20 lakh. And with that 5+ years of experience, you are in the team lead position with a package of 25 to 30 lakh. And with the 10+ years of experience, you are in the team manager position with a package of 60 to 80 lakh. So this is an industry salary scope is there in the VLSI industry. So placement at Takshila VLSI. So placement support. So in our institute, how we are supporting the placements and all. So first we are tied up with the 200+ hiring companies. So including product, service and startup. So MNC companies such as L&T, Capgemini, HCL, Wipro, AMD, Snipers, and many more service companies are there. Tool and interview support till get placement, and 4 to 6 lakh package will be the minimum package, and we provide the 100% placement assistance guarantee. So placement process, how we will do the placements of the students. So first we get the requirements from the client. So what are the jobs are there inside the company? First we get that requirement. After that we assist the student in the preparation of the resume as per the requirement, and we send that resume to the prospective clients, so who are hiring, and shortlisted candidates to attend the interview. So it may be a written test, technical round, so group discussion. So based on their company interview process, they will conduct the interview. After that, we'll announce the final selection. So that is a placement process is there in our institute. So gateway for semiconductor industry in Takshila VLSI. We are tied with the 200 plus hiring companies. So in that 200 plus hiring companies, we have the Tech Mahindra, Qualcomm, Digicom, Wipro, Cadence, Capgemini, so Synopsys, L&T, HCL. So these all are the top companies are there with our institute. Other than this, many more service companies, startups companies are tied with our institute. So 2024 place students. So these all are students are placed in the 2024. So these are the students are placed as a physical design engineer, as an analog layout design engineer, ASIC verification engineer. So in the company is called Cadence, Excel VLSI, New Silicon, so Tessar Semiconductor. So in that all the companies of students are placed and working now. So one of our students placed in the company called On Semi with a package of 12 lakh per annum. So it is an industry highest salary package for freshers. And Abhimanyu Kumar, his place in the Synopsys as an analog layout design engineer. And Utti Bhavesh is his place in the Micron with a package of 12 lakh per annum. So it is also highest salary package for freshers. So you can see here, so these all are the students are placed in the multiple VLSI companies. So these all are the students are placed as a physical design engineer, as an analog layout design engineer, a SIC verification engineer. So in the company is called Blueberry. So and Insemi, Capgemini, Digicom. So in the almost all the VLSI companies, our students are placed and working now. So you can see here, so these all are the students are placed in the multiple VLSI companies. So other than this, many more students are there. So they are got placed in the multiple VLSI companies. So 2024 place students company wise. So in the Capgemini itself, 13% students are placed, and in the L&T Technology Services, PTF Semi, HCL, Tissol Semiconductor, and in Snipes, Cadence, Bitsilica, and Chris Semi, Maven Systems, so and Tansila. So in the almost all the companies of students are placed and working now. So if you need more information about the course structure and fee structure, so you can visit the office. It is there in the Bangalore and Hyderabad location. So otherwise you can contact through the phone number, mail is there, email address will be there, website is there. So you can contact with any one of this. So this is a contact information. So we will start the technical part. So still now you learn that how the that IC will be fabricating. So what are the companies are there? So how the growth will be there? So about our institute. So about placements. So everything you learn. So still now from now onwards we learn that technical part. So technical part means what are the ICs are there? So how we have to fabricate? What is the process we have to follow in the companies? So what are the terminologies will becomes in the designing the IC. So everything we learn from now onwards. So we'll start that one. So that is an analog or AMS and digital design flow. So first is types of an ICs. So whatever the ICs are there, so in that ICs mainly we have the two types of an ICs. So one is an analog and mixed signal ICs. Other one is an digital IC. So what is meant by analog and digital ICs? So I think you already learn analog circuits and digital circuits. So that input, whatever that inputs it will be taken by that circuits, it will be different. For example, so you take the analog and mixed signal ICs. So for that analog and mixed signal ICs, it will be take the all the possible values within the range. For example, 1 to 2 you are giving the input, then it will be take the all the possible values from 1 to 2, like 1.1, 1.2, or a 1.01, 1.02, 1.03, 1.04, so up to 2.00, like this every possible value it will be take, and it will be produce the output. So that output will be like waves format. So every single inputs, it will be produce the output. So whatever the simple chips are there, so that will be designed by the analog and mixed signal ICs. That we have the audio processing, memory, sensors, power. So that all will be designed by the analog and mixed signal ICs. And come to digital IC, so it will be take the values 0 or a 1. So any one of these two values only it will be took. So it will be called as a binary numbers. So you know that. So whatever the flip-flops is, so latches, it all will be comes in the digital circuits only. So whatever the complex chips are, so that will be designed by the digital. So we have the processors, wireless USB, Bluetooth controllers, so that all will be designed by the digital. So we'll see how we will design the analog and mixed signal ICs and how we will design the digital ICs, what is the process will be there. So first we will discuss about the analog IC. So in the analog IC, we have the two steps. One is the front end and back end. So in the digital also, we have the front end and back end. So but inside that steps will be different. So in the front end, we have the analog circuit design. In the back end, we have the analog layout design or a custom layout design. So we'll see what we will do in the front end and what we will do in the back end. So this is in a flow we have to follow for the analog IC design. So first one is in a front end we have to follow. So that will be done by the analog circuit design engineers, and back end will be done by analog layout design engineers. So in this word only you can understand. So in the front end, we have to design the circuit. In the back end, we have to design the layout. So that circuit, we have to convert it into a layout. In the circuit means it will be like logical connection, symbols of the gates. So that will be there. But come to the layout. So it is in a particular area. In that particular area, cells will be placed. So the connections will be done based on the physical connections. And we use the metal layers to connect. So physical means not we will do by hand, it's the software only. So the physical connections we have to do. So in the logical connections means that connections will be go like this, go like this. Like this means it will be not a problem in the circuit. But when you come to in the layout or in the physical connections, that connections should be proper. So that will be go straight line only. So that not crisscross will be happen in between the connections. So we have to take care everything and we have to design the layout. So in the front end, the first step is schematic design and simulation. So what is mean by schematic design and simulation? So whatever the design we are designing or we are fabricating the IC, for that one, first we have to draw the schematic view. Means for example, you are designing the inverter means, for the inverter, how we will design the circuit diagram using a CMOS. So this is a circuit diagram or a schematic design. So we have to use for the inverter. So this is a schematic design. So first we have to do the circuit. So you can observe here it is there. So after that we have to do a simulation, means by observing the waveforms or by observing the any like a truth table. So anything we have to use and we have to do the simulation, and if the specifications are made, then we come to the backend phase. So when you enter to the backend phase, so we have the steps called placement and routing stage. So what is meant by placement and routing? So placement means already said that in the particular area we have to place the ICs. For example, inverter means one PMOS we have to take and one NMOS we have to take. So we have to connect. So this is a poly. From this we are taking the input. It is a source drain. So this from this we have taken the output, and here we are giving to the VDD, and here we are giving to the VSS. So this is a layout. So first is in a placement means we have to place the cells. After that we connected with the metal layers. So that is called as a routing. So after routing stage we get the layout. So this is a layout we get. So for this layout we have to do checks. So that layout will be correct or not, we have to check, right? For that one we are doing the DRC check. So DRC means design rule check. So what is mean by design rule check? So whatever that fab companies are there, so they will give some design rules. So if you not follow that design rules, that IC will be damaged. So you have to follow that design rules for the fabrication process. So that rules we have to give here only. Means for example, if the two metal layers are running like this, so we have to maintain the minimum spacing between these two. So why we have to maintain? So what happened if you not maintain the minimum spacing means, So that whatever that surface of the metal layer will be there, so that is not exactly like this straight line. So it will be fabricate some notch like this, some notches will becomes outside. So somewhere that electrons will be more, so somewhere that electrons will be less. So like that it will be fabricate. So what happened if you not maintain the manufacture minimum spacing means, so this two will be short. So because of the spacing will be not there, so that's why it will be short. So it directly damage the IC. So that's why we have to maintain the minimum spacing. So other than this, we have the tools called minimum width, maximum width, pitch of the metal layer, some area rules are there. So these all the rules we have to follow to design the IC. So after that DRC, we have the another check called, so I will explain here only, another check called LVS, layout versus schematic. So what is mean by layout versus schematic? So after the routing stage, we get the layout, and here in the front end, we get the schematic view. So this is a schematic, so this is a layout. So we have to compare layout and schematic, like the number of the connections same or not, that connections must be same. So here you are using 100 connections means in that layout also it will be 100 connections will be there. So that number of the cells must be same. So that we have to check in the LVS stage. And parasitic and LD extraction, post layout netlist simulation. So if the specifications are made, then the analog IC design flow will be completed. Otherwise, we have to do from the schematic. So this is in a complete layout and schematic open op-amp. So this will be the schematic. So this will be the layout. In the schematic, you can observe here so symbols of the gates and logical connections we are used. So in the layout, you can see that proper placement of the cells and connections will be happen. So this is a schematic and layout of the op-amp. So come to digital IC or ASIC design flow. So here also we have the two steps, front end and back end, but some steps will be same as in the analog IC design flow we are following, in the digital IC we are following. But compared to the analog IC, so here in the digital IC to design that one, we have the more steps compared to that analog ICs. So digital IC also called as an ASIC design flow. ASIC means I already explained. It is application specific integrated circuit. So whatever that IC is there. So whatever the ASIC or a digital IC we are using. So to fabricate that IC, we are using permanently connected gates and flip-flops. So the logical function cannot be changed. So what happened if you not use that? If you not use that permanently connected gates, so you want to do from the scratch, means you want to learn, so you will start doing from the scratch. So what happened in while doing? So if you miss any connection or any cell definition or anything you miss means the directly damage to the IC. So that's why what the digital IC engineers will be do. So they will take already connected flip-flops and gates. So in that IC means mostly we are using gates, flip-flops, so gates, flip-flops only. So better we have to take permanently connected gates, means they already connected, means analog standard cell design engineers are there, no? So they particularly they will design it all the standard cells and they will verify everything. So again, why we have to do from the scratch? It will be simply time wasted. So that is why, so we have to take the permanently connected gates and flip-flops and we have to do the design of the IC. So in the next slide, so while explaining, you will get to know what are the permanently connected gates we are using. So nowadays ASIC has a completely system on it. So system on it means nowadays one IC, small IC, it will be enough to do every function like audio, video, memory, ALU. So everything will be done by that small IC only. So that's why it is called as a system on chip, SoC. So come to the flow of the digital IC or ASIC design flow. Here also we have the front end and back end. So in the front end we have the RTL design. So it will be mainly related to the code format. So and when we come to the backend phase, so in that backend we have a logical design and physical design. So two are there. So in the front end, first step is design specifications. So what is meant by design specifications? So design specifications will be given by the end customers. So based on the market requirements. So who are the end customers? So for example, I am the customer, I want the IC for the particular function. So I have some business and everything. So I need the IC to do that work. So I will come to you and I will explain. So you are the designing of the ICs. So, so based on the area, timing, power, and speed, I will give the specifications. So you have to note down all the specifications and you have to start working on that. So you have to write the code, verify the code. So we have to design the IC and verify that IC. So then you have to do the manufacture and then you have to provide me. So these all the steps we have to do. So after receiving the specifications, we start writing the code. So that one will be done in the RTL description. So in the RTL description, we are writing the code in the hardware description language. So what are the hardware description languages are there? So Verilog or a VHDL. So any one language, so we have to use and we have to write the code. So that one will be done in the RTL description. So after the RTL description, must and should we have to verify that code. So that one will be done in the functional verification functional verification. So after these three steps, so we will come to the backend phase. So when you come to backend design, so you start using tools. So here still now you write the code for the design. So when you come to the backend phase, we use the tools and we deals within a cells and gates. So that code format will be not understood by the tools. So that must and should we have to convert it into the gate format, means that to design the IC means we need the gate information only. So that how that gate will be formed and how that connections will be happened from the gate to gate or inside the gate. So every we need like in the gate information only. So that code information is like a logical connections it will be explained, like so it is a AND gate means so you have to give the 0 0 input means it will be produce the 0. So 0 1 means it will produce 0. So like logical connections will be there. So we just know what we give input and what we get output. So when you come to the backend phase, so you have to explain how the data will be transferred from the one gate to one cell to the another cell. So inside it will be how it will be transferred, what is the delay we have to consider for that cell, everything. So we need, so to get that one, so we have to get that gate information. So to get that gate information, so we have the process called logical synthesis. So I said that to do the synthesis, we are using tools called Genus and other one is DC compiler. So using any one of the tools, so we have to write the code. Sorry, we have to convert the RTL code into a gate level netlist. So that gate information we call as a gate level netlist. It is in the .v format. So this code will be like this model. So something you write an end model. So like this will be there. So this will be not understand by the tool. So what we have to do? So we have to convert to like this. So these are the gates are there. So like this we have. So it is also not structure like this, means it is also not designed like this. So it is also in the code format only, but in the code only it contains the all the gate informations like a delay of the every pins in the gate. So delay inside the inside that cell and net delay, so that cell delay, so everything will be present in the gate level netlist. So to convert from this to this process is called as a logical synthesis. Logical synthesis. So to design that one, so to convert that one, we are following the three steps. So one is a translation, mapping, and optimization. So one more thing in the backend phase, we have to consider it is a technology dependent process. So what is mean by technology dependent? So whatever that front end is, so we are not discuss about any technology. Means we are using the 3 nanometer technology. No, we are using a 5 nanometer technology. No, so that we don't know which technology we are using. Just simply we write the code and we provide to the backend phase. So when you come to the backend, so that time the technology will be a fear. So that like we are designing the 3 nanometer technology means, so based on the 3 nanometer technology only, so that all the gates and all the connections, delays, so everything will be changed from the technology to technology. So in the first step, translation means, so we have to convert this code to the gate information. So but these gates are technology independent cells at the first stage. So that cells will be called as a generic cells. So after that, we map to the technology. So that is called as a mapping. And after that, we do the optimization based on the area, power, and timing. So these 4 steps we have to follow to do the digital IC or ASIC design flow. To convert means it is, I explain only the theoretical form. So in the tool related means we have some commands and all. So first we have to read all the inputs and we have to convert, map, optimize, and after that we have to write that changes. So everything will be done. So that will be about the synthesis. So logical synthesis. So after the logical synthesis, we get the gate level netlist. So using that one, so that for that gate level netlist, we are doing the check called logic equivalence check. So while converting, to some ports will be missed or some gates will be missed, some connections will be missed. So that we have to check in the logical equivalence check. So it will be compare RTL description and the gate level at least, and it will be check. So and after that we will come to the back physical design called place and route. So also called as a PNR. So entire process we called it is a physical design. So place and route means, so whatever the inputs we have, so that all the inputs we have to read. So I'll explain what are the inputs we require to do the design of the IC. So after that we have to estimate the area and we have to place all the cells. So like this, and we have to provide the power to all the cells, clock, and we have to route the signals using the metal layers. So mostly we are using the metal layers from M1 to M9. So some companies use cells metals from M1, M0 to M8. So this M8 or M9, so these are the top metal layers. So that have the more width. So the top metal layers and resistance also less. So this will be used for the connections. So top level connections will be there, means entire design. So we have the boxes. So we'll explain what are the boxes will be there. So to connect that boxes, we are using this higher metal layers, and in between M1 to M8, so some metal layers we have to use for the particularly power and particularly for the clock and for the signals. So like that we have to divide. So that will be done in the routing stage. So these are the steps we have to follow. So after this we get the layout. So layout of the design. For this layout means it is called a physical layout. For this layout again we have to do the verification. So in the analog IC I explained that we do the DRC and LVC. So that checks we have to do here also. Other than that, we have some related timing and power violations also we have to check. So that will be done in the physical verification, and we have to convert that layout into a GDS2 file. So using that file, the fabrication will be done. So that file we have to send to the fabrication team. So that fabrication team will be do the fabrication of the IC. So based on the GDS2 file. So this is a complete ASIC or a digital design flow. So in the ASIC also we have the 2 steps, front end and back end. So in the front end we have the RTL or FPGA ASIC design, ASIC verification, design for test. So RTL or FPGA ASIC design. So it is also it is 3 are same only. So here we have to write the code, and in the ASIC verification, so we have to verify the code, and design for test. So there also we are writing the code, but we write the code for the testing purpose. So I will explain what is meant by DFT in next slides. So after that in the backend phase, we have the physical design and physical verification. So physical design and physical verifications will be comes in the backend phase. So that one also we will discuss in the next slides. So So first step in the ASIC design flow is the specification. So already explained what is meant by specifications. So after getting the specifications and before writing the code, we have another team. So called as an architecture team. So we have the another team called as an architecture team. So that architecture team, what they will do means they will design the architecture. So based on the specifications. So for example, you are designing the home, you are building the home means, so first you will go to the architecture engineers and you will explain how you want the home. So based on that, they will design the architecture and they will give. So like that here also, so we have architecture engineers or architecture team, so they will design the architecture. That architecture may be in the form of block diagrams. So in the form of block diagrams and in the form of flow charts or in the form of spec sheets. So that will be explained how we have to design the IC or how we have to write the code. So based on the specifications, so that will be defined by the architecture developed by the architecture engineers. So after getting the architecture, so we have the RTL team. We come to the RTL design. So RTL means register transfer level. So here we have to use the combinationals and sequential circuits. So we have to use the combinational and sequential circuits. So you already know what is meant by combinationals and sequential circuits. What are the circuits will becomes in the combinational? So like mux, demux, so encoder, decoders, and in the sequential, we have the flip-flops, latches, counters. So using that circuits, we have to write the code in the Verilog or a VHDL. So any one of the language we have to use and we have to write the code. And that above architecture means whatever that architecture will be designed by the architecture team. So that architecture team, we have that architecture we have to convert into a code format. So after writing the code, so we have to verify the code. So that one will be done in the ASIC verification. So in the ASIC verification, so mainly we have to verify the code. So first step is architectural modeling, design specification, functional testament. So these are the normal steps. So mainly that verification of the code will be done in the functional verification environment. So this diagram is there in the next slide. So in that we have the separate method is design under test. So in this design under test, what we do means, so we will provide some input vectors or a test vectors to verify the code. So we have to give some sample inputs. So it will be sample inputs and outputs also we have to give, and it will be get that output only. So in between that any error will become or in that program will be stuck or not, we have to check. That one will be done in the design under test. So that is that all this simulation will be done by the designers and verification engineers. So if the expected result is met, then the ASIC verification will be completed. Otherwise, we have to do the iteration of the verification stages. So this is in a process. This is in a diagram we have to use to do the design of the or a verification of the IC. So first we have the test code. So if you learn already very long means you know how we will write the test bench. So based on the test code. So it is in a test code, which code we have to test. So in the test bench, what we are including? So we are including the clock. Why we need the clock? So if the code is in the sequential circuits means for that sequential circuits we mention the clock, and BFM. So it is a bus for module, so that will be act in between these two for the transferring the data. And unit under test. So in the unit under test, we'll provide the input vectors and test vectors to check the output of the code, and some other models will be there. So this is in a process. So we have to follow to verify the code. So after the verification, we come to the DFT or a design for test stability. So in the simple way, I will explain. So whatever that IC we get after the manufacture, so before providing to the customers or a market, so I said that we will do the testing of that an IC. So to do that testing of an IC means, so that feature or a testability feature or that facility we have to give before only while doing the of an IC. So if you not give means how you will test that IC after the manufacture. For example, you are designing the doll. So while designing, so you have to give that facility to that doll to become a testable after the designing of the doll. So then only you will test that doll, it will be correct working or not. So same process we have to follow in the DFT also. That facility we have to give before only while whatever the testing we have to do after the manufacture. So before only that feature we have to insert in our design. So basically that feature means it is in a code. So that code will be written by the DFT team. That code we are inserting in our design, so it will be help to do the testing of the IC. So why we have to do the testing of the IC after the manufacture? So before manufacture of the IC, so we do lot of the checks. So we have to check about timing, power, so area, everything we check. Again, why we have to do checking after the manufacture? So whatever that manufacture process we are following, so it is not 100% error free. So there are some defects in the silicon which will be damage the IC. So that's why we have to do the testing of the IC again and again. So that one will be done by the DFT team. So once you, if you are interested in the DFT means when, if you take any DFT course means, so you'll get to know that how the DFT will be work. So in that we have some stuck and fault models. So we have to introduce some errors and we have to do the check. So everything will be done in the design for testability. So it is a last step in the front end. So after this, we will come to the back end phase. So in the back end phase, so we have the physical design and physical verification. So physical design means, so whatever the physical design means, we have to convert circuit information into a layout. So in the circuit information it contains the logical connections. So that we have to convert into a layout. So in the layout, it will be, so in the layout, it contains like physical information, how that cells will be placed, connections will be there, so that all the information will be there. So here only I will explain entire that digital design flow, physical design flow, and next slides you will get to know. So what is the steps I discussed before only. So the first step in the physical design flow is partitioning. So partitioning means, so you said that the IC, it contains the system on chip, means all the systems will be there in a one IC only, like audio, video, memory, ALU. So these are the four functions that this IC will be do. These are the four functions will be there. So that entire these functions, including entire these functions will be there in a one IC only, means it will be called as a full chip. It is an entire chip. It will be do every function. So in the partitioning, so we have to divide this IC into sub blocks. So for the each block also we have to design. So it will be doing some audio process, means to do this audio process, for that one also we have to design that IC. So we have to take this block. For this block, we have to do the physical design. For the entire chip also we have to do the physical design. For the every blocks we have to do the physical design. So after completing the for the every block design, so we have to place all the blocks inside an area and we have to give the connections. So the first step in the physical design is floor planning. So in the floor planning, we have the two types, full chip and block level. So first we discuss about the block level. So for the each block, we have to do the floor planning. So in the block level, first we have to estimate the area of the block. So area of the block. So this area, so this block area, we have to estimate. So that will be estimated by based on the macros and standard cells. So what is meant by macros means these are the cells or a blocks. So they are permanently connected. So we can't change this functionality of the blocks, also called in a black box. So and standard cells means AND gate, OR gate, inverter, buffers and all. So that will become the standard cells. So using this count of the macros and standard cells, based on that only we have to calculate the area. And after that we have to place all the pins, and we are placing the macros. After placing the macros, we have to provide the power to all some physical only cells also we are using. So physical only cells means, so they don't have any functionality. So to reduce some issues, so we are using the physical only cells. So once you get the physical design course means you will get to know what are the physical only cells are there. So these steps will becomes in the block level. So after these steps, so we have to do the placement stage. So in the placement, we have to place the all the standard cells, and after that we have to do the clock tree synthesis. So in the placement stage, we have to do some checks after the placement stage. After the floor planning also, we have to do some checks like that macros will be placed correct or not, in the pins are correct or placed or not, we have to do. The placement stage, after placing up the standard cells, mainly we are checking the issues called congestion and timing. In the timing also, mainly we are checking that max trans, max cap and setup. So congestion means, so if you that this is an area is there, so in this area you mentioned that 25.25% of the cells will be placed. So suppose, so more than this cells will be placed like this 0.5 percentage place means, so in this area that area will be congested, so that not they not get proper power to receive. So proper power it will be not received by the metal layers, so it will be not do proper work also, so that is a congestion. So it is not receiving proper power from the metal layers. So because of that congested area means, because of that small area lot of cells will be placed, so that is a congestion, so we have to reduce. And in the timing, max trans, max cap and setup value, so these values we have to give in the one file. So if that value will be exceed, so then we get this violation, so that we have to reduce. And clock tree synthesis, so we have to provide the clock to all the sequential cells. So we have to do here congestion issue also, congestion check also, max trans, max cap, setup violations also, and other than that we do the hold violation. And in the routing, so we have to route the signals, so using the metal layers. So after the routing stage, we do the checks called congestion, and these all checks we have to do. So other that DRC, LVC, LVS, ERC. So these are the checks we have to do. So this is a complete what physical design flow. So I explained what is meant by physical design flow, and the main aim of the physical design engineer is to generate the layout with a minimal area. The first step in the physical design is a import design. So we have to take I forgot to explain about the pull chip. So here pull chip means, so after completing the so where it is pull chip, here there in this one. So pull chip means after completing this all the steps for the each block, so all the blocks we have to place inside the one area, and we have to give the connections and that external pins whatever we get, no, so that golden bonds are there, no, so that we have to connect it to that all the entire IC. That is in a pull chip. So inputs, what are the inputs we have to use? So first one is a gate level at least. It contains some macros, standard cell information, how the data will be transferred, and that some delay informations. So that will be there. And consent means clock information will be present. So what are the clocks we have to use in a inside the design? Logical and physical library, it mainly contains timing, power, and area. And DEF, design exchange format. So it contains the physical information of all the cells, pins, layers and all. Scan depth, so it contains the scan chain information. So this one will be get from the DFT team. So that DFT team write some code, right? So that is in a scan depth. And the UPF file, so that is in a contains the power information. So for the multi-voltage means some cells are working the different voltage, some cells are working the different voltage. For the domain, so we have to mention the different pins and connections. And after this, we have to read some initial checks. So we have to check that all the inputs will be correct read or not, like check netlist for the netlist file, check timing for the constraints, like that we have to do some initial checks. So this is an so while doing the import design, so we have to create one Milky Way library, and we have to read the netlist file. So using the script, so after reading the script, so you get this layout. So this is a layout we get. So this is in a block area. So inside this block area only, we have to place this all the macros and this all the standard cells we have to place. So only when we read the inputs means we get the information, means what are the informations we need to design the IC, so that we get. But placing and creating everything, so we have to do. So these macros we have to place, and this standard cells we have to place. And we have to create one scenario using the script. Why we have to create a scenario means, so our chip must be working the all the condition and all the temperature. So that's why we are creating the scenario. And using the star GUI command only, this layout will be open. So otherwise it will be not open. So we have the floor planning and power planning. So I already explained what is meant by full chip and block level. So in that we have the core limited design. So based on number of the macros and standard cells area, we have to estimate the core area. So this is an layout we get after the floor planning and power planning stage. So you can observe so that all the macros are there at the corner in the input design. So now you see so that all the macros will be placed inside the core area. So to place the macros, we have some guidelines. So we have to follow that guidelines and we have to place. So we will do the manual placement. So here that one macro we will take, and that one will be moved to the where we will move to inside the design, inside the layout where we have to place. There we have to place at all the macros. That one will be done in the floor planning and power planning stage. And menu bar, toolbar, activities, tool settings window, and settings window. So these are the sections of this layout. So after that we have the placement. Placement means I said that um, we have to place all the standard cells. So using the command called place oft, so that using that command we have to place all the standard cells inside the core area. So to place the standard cells, that tool consider the connections between the standard cells and macro standard cells and standard cells and IO port communication. So based on that all the standards will be placed. So that here that the placement will be done automatic placements. So based on the connections, and here we give more importance for the timing and congestion. So because after the placement stage we get the lot of the timing and congestion issue. So consider that one, and we have to do the placement stage. And placement goals are less utilization jump, no congestion, no overlaps or legality issue, and good timing values. So this is in a layout after the placement stage we get, and that is in a script we have to use. After the placement stage we have the clock tree synthesis. Clock tree synthesis means we have to provide the clock to inside the design for the sequential elements. So main clock we have to define. From the main clock we have to distribute the clock inside the design. So distribution of the clock will be done by these classifications: clock tree, clock mesh, and clock spin. So this is a main clock. So that clock will be divided, subclocks is again divided and give to all the leap cells. So to dividing the clock, so we are using the cells called buffers and inverters. So this is a clock tree synthesis. So to do the clock tree synthesis, we have to define some rules that are necessary to define. So like a routing rules, we have to define means what are the insertion delay we have to set. So and the clocks, which are the clocks cells we have to use. Mainly we are using buffers and inverters only. And which metal layer we have to use for the routing the clock, so that we have to define. And using these two script only, we have to do the clock tree synthesis. And after the clock tree synthesis, we come to the routing. So routing means, already said that we have to route the signals, except power signals. So we have to route the data signals and clock signals. So why except power signals? That power signals already routed in the power planning stage. So except that power signals, so we have to route the data signals and clock signals here. So we have to give the electrical connections using the metal layers and wires. So these are the 4 steps we have to follow for the routing stage. So global routing, track assignment, detailed routing, and search and replace. To explain these 4 steps means it will be take more time. So these are the 4 steps we have to use for the routing stage. And to do the routing stage, we have to do some pre-route checks. So using the command call check the data routability, we'll get to know how many outer boundary ports are there, minimum gridders are there, block ports are there. So this is a script we have to use for the routing stage. So after the routing stage, we get the proper layout. For that layout, we have to do some checks like a formality checks. So LBS means layout versus schematic. So already said, here we are getting some opens and shorts violations that we have to reduce. And DRC means design rule check, like some minimum width violations, maximum width violations, like that we get. And timing analysis like setup and hold violations, design rule violations like max stance, max cap violations. IR drop analysis like power will be dropped in the inside an area. So for that because of the metal length, so that we have to reduce. So these are all the checks we have to do after getting the layout. So if you not do these checks and you will directly move to the manufacturer of the IC, means that IC will be damaged. So that's why before giving to the manufacturer of the IC, before going to the manufacturer of the IC, so you have to test this all the checks. So this is in a last step. So in physical design or in the ASIC design flow, after this we have to do the design of the IC. So I did from my side. The students, you have any doubts, so any queries related to technical and non-technical part, so you can ask the questions. We'll clear that one. Otherwise, we'll end up the webinar today. Okay, students, you don't have any doubts means we will end up the webinar today. Thank you.
Good evening, everyone. A heartfelt thank to our speaker Apurva ma'am for sharing their valuable insights. I would also like to thank HODs and students for their efforts in making the webinar a success. Looking forward for such a more interaction. Thank you.